2?
So,
on that little quiz you showed us.
looking at our M plus and the M plus 2. Okay, so let's define first what the M plus means. What is the M plus? Okay, it is the molecular ion. So it is not spelled that way, but it's the molecular ion signal. So what we're saying is we took the compound and we removed an electron. If a compound loses an electron, what charge does it become? Positive. What is its mass? The same as where it started. Okay? That is your molecular ion signal. Okay? Remember, what we're looking at is our mass. Different elements have different isotopes and differing amounts of isotopes. When we look at hydrogen, there's 3 isotopes. Okay? We have hydrogen with 1 proton, no neutrons. Then we have deuterium with 1 neutron, and we have tritium with 2 neutrons. So we end up with a total mass of 3. Okay? If we took the average mass of those 3, what would our average mass be? What is the average mass of 1, 2, and 3? 2. The periodic table tells you your average mass. It is not telling you it is 2. Why not? It's a weighted average. When we look at a random sample of hydrogen, 99% of it is atomic mass 1. So that if we looked at a random compound that had hydrogen in it, 99% of the compound where it has hydrogen would have 1 mass, okay, or the same mass. 1% of it would have a single deuterium in it, which means the mass would be plus 1. Why plus 1? 1 more neutron, 1 more mass unit. So when it comes to hydrogen, we tend to not look at an isotope effect because 99% of it is hydrogen, or is single proton. Okay, no neutrons. We could do our mass effect or our isotope effect when we look at carbons. Okay, but 99.5% of it is carbon-12. So again, we don't see a real mass effect when it comes to the mass spec. There are certain elements that have more common isotopes. Those we will see a mass effect in the mass spec. The primary one, bromine, because there are 2 common elements of bromine, or isotopes of bromine. Those common isotopes are
79.
bromine 79 and bromine 81. If we take a look at our average, this is awesome having a periodic table, our average molecular weight now for our bromine, 79.9. Not 79, not 81. It's roughly 80. What does that mean about the 2 common isotopes? They're roughly 50-50. So when we look at a mass spec, a random sample of bromine being attached to a compound, half of those compounds will have element 79, the other half will have 81. So when we look at the mass spec, we'll see 2 peaks. Okay? And they will be separated by 2 mass units, because it's the 2 neutrons. Those 2 peaks will have the same intensity, if bromine is present. If bromine's not present, do we expect to see an M plus 2?
No.
No. Okay. There's one other element that you're responsible for. Chlorine. Chlorine is composed of 2 common isotopes as well. Chlorine 35 and chlorine 37. Based on our atomic mass, our average atomic mass on the periodic table, it's 35.4. Okay. Are they in there in an equal ratio? No. Which one's in there in a higher ratio? I'm going to send you all the way back. You got it? Okay. Chlorine 35 is in there in a much higher ratio than chlorine 37. It just so happens that it is roughly a 3-to-1 ratio. So we'll end up seeing the intensities there. There are other elements that have similar effects, and we could look at them, but this is organic chemistry. Most of the elements that have those other effects, not organic because we don't care about them. Okay? By all means, feel free to look at them. You can spend the time on it. That's not what we're doing in the class. So having an M plus 2 does not mean it's 1-to-1. Having an M plus 2 that is 1-to-1 means bromine is present in the molecule. Okay? Other questions? Okay. So sorry, I meant to have these all in there. in the proper order. So now we're going to have to kind of jump ahead. Whoop, there we were. So our multiple stereocenters, we talked through this slide. Were there questions on this one? We looked at the relationships for all the possible isomers for our dichlorocyclopentane. We looked at the possible stereoisomers for chloramphenicol. Okay. Everybody okay with that? Okay. So we'll start right back up with more questions. Identify the relationships between all of these compounds. So just like we did with Earth, we actually have 1, 2, oh, I can't count. A, B, C. It's 4. We have 6 questions up on the board right now. Okay. You are being asked to identify the relationship between the top 2, which we've called the relationship A. We're being asked to look at the relationship between the left 2. We're calling that relationship B. The bottom 2, C, right 2, D, and then our crosses E and F. So there are technically 6 questions on the board. This is 6 exam questions. What I would do is give you 2 of those structures and say, what is the relationship between these 2 structures? And then you'd have a list of multiple choice options. One of the things that I got kind of mean on here, though somewhat unintentionally, is that I didn't list all the possible options. So let's see if we can do this through a mild shout out. What are our possible options? Diastereomers, yes. I heard enantiomers, though I should have done meso because those are, oh gosh, that's close enough. Meso, different, structural, and identical. Is that all of them? I think that's all of them. I knew you were going to do that to me. Enantiomer. Right. Where this type of question would show up is strictly in the multiple choice because there's really no work to show those relationships. So you would see it in a multiple choice. You'll notice the possible answers. We have 1, 2, 3, 4, 5, 6. If you remember from the exam, how many possible answers do you get in your multiple choice? Only 4. So I would probably pick 4 that are the most similar to each other for any of these individual questions, and then eliminate the other 2. I'll tell you right out the gate, meso and identical I would not put as 2 separate answers. Not intentionally. It may slip through. Why would I not put meso and identical in the same answer choice? Meso and identical are very close to the same thing. You can have 2 compounds be identical but not be meso. But if you have a meso compound, they are identical. Okay? So they're enough of a gray area that I would never give you both of those answer choices intentionally in a multiple choice. Okay? Typically what you would see would be meso/identical. Okay? Showing that we are kind of guiding you to the point that they are the same thing. Okay? So we're going to start with E. Kind of arbitrary, well not arbitrarily because the group at front was talking about it. What is our relationship on our diagonal, which we've labeled as E? Okay. So we've heard a couple answers here. Number 1, I heard different. Number 2, I heard diastereomer, which I'm just going to write as DIA. And structural. Interesting. Can the relationship possibly be all 3? No. So unfortunately, 2 out of 3 people are wrong. Okay. This is difficult to go through and process and figure out what's going on with it. Okay. So those that said it was different, why did you say it was different?
Doesn't the one on the bottom have a CH3, an extra CH3?
We have this apparent extra CH3 in the bottom that does not appear to show up in the top. We don't see it there. Okay, so you're right, it does not appear to be there. It looks like we've added it. But what else did we do? We took one of the CH3s away. Okay. So what we have actually done is exchanged a CH3 for the H as far as locations go. So we've just changed the numbering, the numerical arrangement of where our groups show up, which then puts us not as different, because for it to be different, we have to have a different formula. We're going to have the same formula. Okay, so it can't be different. Diastereomers, okay, well, they are non-superimposable, but when we get to diastereomers, we have to make sure that the atom connectivity is all the same. This methyl group has changed its atom connectivity. It's either being attached to the ring carbon or out off of a substituent. So it can't be diastereomers. This then puts us at the structural isomers. We've changed the location of where the atom is located. If I can say location another 4 times, that'd be awesome. Okay? Now let's move up to A. What do we get for A? These are going to be our diastereomers. Okay. We do not have atoms changing locations, okay, or atom connectivity changing, but what we do notice is that we are changing our wedges and dashes. Okay. For them to be mirror images, so let's take example hand. If I take the mirror image of my right hand, it would become my left hand. Okay. Madeline, I need you to hold up your hands. Give me your right hand. Okay. If we take the mirror image of our right hands, what do we get? My left hand and her left hand. What if we got my right hand? I can't duplicate. Are they now mirror images? No. One of the positions did not mirror. So when we're looking at, you can put your hands down. When we're looking at a structure with multiple chiral atoms, okay, to be mirror images, both of them must exchange their location. Sometimes it's more obvious than others. In this case, it's a little bit more obvious because we've left the ring in the exact same location. We didn't do any flips or rotations of the ring. We just kind of mirrored or drew it exactly across. So everything overlaps except for those 2 positions. Okay? The carbon, that carbon there, if we look across between those 2 structures, did mirror. Went from a dash to a wedge. Okay. If we look at the next carbon that was a stereocenter, it was a wedge and it went to a wedge. It did not mirror, which means it can't be enantiomers. And since we followed all of our patterns all the way through, we're now left with diastereomers. Okay. B. What's our relationship in B? Sorry, I started cleaning things before I could look at it. And B helps us out, actually. And that relationship we just talked about. Notice that the ring did not change location. We didn't flip it, turn it over to make it more confusing. Okay. We just drew the same ring structure, and what happened to our carbon with the alcohol attached? It went from dash to wedge, right to left. What happened to our carbon with the sort of isopropyl? It went from wedge to dash, or dash to wedge, depending on which way you're going at. So it mirrored, which means enantiomers. Both of them mirrored. Questions about that? And hopefully it'll pop up. No, just deleted my work. Awesome. So far, so good? How about C? Okay, C is going to put us in the exact same boat that F did. Okay, we've changed the location. So we have a structural. Just for the sake of being obnoxious, we could also call that constitutional. Same thing. Okay. Why would we pick one or the other? You'll notice I picked structural. Any guesses why? Fair enough. It is easier to spell. I was going to do a little less self-deprecating humor, but that's pretty close. Constitutional has too many letters. Okay. Structural is a little bit easier to write, faster to write. Okay. Really no difference as far as our labeling between those. D, which was supposed to be in green but never shows up on our projector. Structural / constitutional. Remember the same deal. What do we have left? F? F, diastereomers. Kind of get it? Okay. I'm now going to attempt to add one more question on here. So I'm going to clear everything. Are we good clearing everything? Okay. I'm going to clear everything. oh, let's see if I can do this right. And I will undoubtedly do it wrong, but we'll see what happens. What's our relationship? So this becomes more difficult. Why does this one become more difficult? Okay, we've done a rotation of the structure as well. If you have trouble seeing it, I freely admit I do. Okay, I hate this section because I have to draw a stupid amount of structures to be able to visualize it properly. What I would try and do is get the bulk of my structure to match, or the structures to match. So it doesn't matter which one I pick, but I will try and make one look as much like the other as possible. So if we look at my red drawing, it looks to me like what I could do. Oh geez, man, I really did make that confusing, didn't I? No, I didn't. If we just rotate, I was hoping to make it worse actually, sorry. We could just rotate in the plane, that direction. And then right?
Erase the white stuff on top of the one that's already done.
Erase the white stuff?
Because you know how you when you erase the stuff that's pre-printed on there?
Oh,
it's just
I see what you're complaining
going
about.
over it in white. You could just...
Oh, I see what you're saying, yeah. And now we've got it where I can then overlay and see the relationship. What happened? All I did was mirror. Okay. If you can see that in 3 dimensions, you could do those rotations without having to draw it. Screw you. Okay. The more complicated the question, the more often these things will get switched and rotated and pulled out of plane. Okay. The extra thing that we could add to this, and let me delete everything on here. Okay, one more kind of rough example is what is the relationship between
The CH3, right?
those are CH3s, yeah. What's the relationship now?
Same.
Okay. So let's flip this. Make this a little bit more difficult. Whoops. There it is. To answer this question, what do you have to go through and do? Those of you good with 3 dimensions are doing all sorts of flips and rotations in your head. And again, screw you. For everybody else, we need to make sure that we're looking at these 2 structures in the same view. Which is easier for you to visualize? The overhead. So that means we should take the Newman projection and turn it into an overhead. So what I'm going to do is set up my eyeball looking from the top. That is an eyeball. You can see the iris. There's some color in there. There's some blood vessels. When we look at that from the top, we'd have our methyl groups now coming out on the sides over here. Well, now we have to be careful in labeling whether they were wedged or dashed. Okay. This carbon was our front carbon. So when we look at the overhead view, that ends up being this one here. Everybody see that? So the methyl group, the first methyl group that we encounter is which direction? The blue one I underlined is now wedged or dashed relative to the eyeball. It is wedged. It is coming up at the eyeball. If we look at the next methyl group, it is dashed going away from the eyeball. Now that we've got a proper view of that model, we can now compare those two structures. If we go through to compare them, what do we notice? Okay. One was wedged and it became dashed. The other one was dashed and it became wedged. Okay. You can attempt to do any rotations you want. You will find they will still not superimpose. They are mirror images. They are non-superimposable mirror images. Okay. And that visualization of seeing that there's nothing you can do to get them to superimpose is not easy to visualize. This is where having the model kit can help out. Okay? So our relationship is now enantiomers. You are responsible for being able to look at the Newman projection. You are responsible for being able to look at the chairs. You are responsible looking at the overhead view. You have to be able to convert between any of those three, even when it comes to harder questions looking at chirality. Okay? Questions about that?
Can you do an example of just a chair?
Chair. Let's see what I can do with a chair.
I need like 6 model kits.
What is the relationship now between these two structures? Change my mind, that's too easy. Oh, crap. And there. I think I got that. Relationship between these two structures.
Draw the overhead first.
Convert it to our overhead. Set up an eyeball can be helpful. This time you haven't had enough coffee or too much coffee. Okay. When we're looking at our overhead view, it's just deciding where your atoms are located. Okay. I would probably pick this atom being the same. Where's that methyl group aimed? So we've got here and here. It's aimed primarily up, which means in our drawing it should be wedged. Where's the other methyl group? Dashed, going away. What's the relationship between our structures now? They're mirror images of each other, which then means they're enantiomers. Okay. How many people saw that relationship from the get-go? Yeah, that's what I thought. Okay. This is where drawing the structures can come in handy. For those of you that didn't see the mirror image right away, okay, and this is what I would do as well, is I would rotate this structure. As we rotate that in the plane, we'd end up here. If we draw a mirror plane, oof, that was a pretty ugly mirror. We know the relationship between these two are mirror images. What is the relationship between those two? Identical. Can I superimpose? That says identical. Can I superimpose these two? That says super. That spelling thing is coming back to haunt me. I cannot superimpose. So they are no superimposable, and they are mirror images, which means enantiomers. Okay. So to solve this problem, what you see up here is exactly how I would solve it. How much time did that take? A long time. Guess when I answer this question? Last. Right? I may know how to do it, but I know it's going to take me time. Skip it. You don't have to spend a lot of time on individual questions. When it comes to your test, 2 minutes. Okay? I'm a little bit more lenient than that. But if you're spending more than 2 minutes on any question, you've spent too long. Move on. 2 minutes should be your cap. Yes, that is an incredibly short amount of time. That's where practice comes in handy. You can start to skip some of these flips and rotations and mirror image drawings. Okay?
On the suggested problems, are there problems where you go from the Newman to the overhead for this?
You can go from a Newman to an overhead, yeah. Oh, for suggested homework?
Yeah.
I have no idea. It's easy enough because there's Newman projections drawn. Just draw the overhead view of that Newman projection. You won't have an answer key provided for you, but you could bring it to me and say, hey, dude, are those the same? And you'll probably watch me spend 5 minutes trying to solve your work. Yes, but that's how this section goes. Okay? Questions about it? Okay, so remember when we did Lewis structures, we looked at Lewis structures, proper bonding, all of that still comes to play. Everything we did on exam 1 is still transferring across into exam 2. Okay, you still need to be able to manipulate those structures. So here's another example. Let's go ahead and fire. Well, actually, we're going to just continue on anyway. But when we looked at our identifying relationships here, where did we keep our primary focus? Okay, so we looked at this part of the ring.
No, towards the
Should have noticed that we were keeping it towards our stereo centers. How did we know we had a stereo center there?
4 different atom connected.
4 distinguishable groups, but I don't see 4 groups attached to any of those. How did you guys know to look at those positions and be like, I think that's a chiral atom? There's another piece of information that might be tipping you off. Okay, we could assume H. Okay. What is different about this last structure in comparison to those?
There's no double bond.
Wedges and dashes. The wedges and dashes were the primary thing we looked at to find our relationships between enantiomers, diastereomers, and all that. We still had to take a look at the rest of the structure, but we kept our primary focus at the wedges and dashes. Why? Because when we're looking at stereocenters, it's the arrangement of atoms around an individual carbon, which means we have to look at the three-dimensional structure. We have to look at wedges and dashes. So if we see a wedge and a dash, there's this little thing that triggers off in the back of our head, that's a chiral atom. But we have to be careful. What defined our chiral atom? 4 different things. Okay. So when we go back to our examples here, in that first one, what do we see? We see 1 stereo center at that position. We have 4 distinct groups. We have that carbon, we have a hydrogen, I'm just going to number them arbitrarily. Then we have another carbon. Why is that third carbon different from carbon number 1? We've got a couple different answers. One, that's a CH2 at 3. Carbon number 1, or whatever we labeled 1, is a CH3. Those are definitely different. Okay. The better approach, or the better answer to that, is that 1 was only connected to hydrogens. Position 3 was connected to a carbon. That is an important distinction to make when we look at nomenclature. Okay. If we look at our last carbon, why is carbon number 4 different from 1 and 3? It has the double bond. The hybridization is changed. So immediately we can say that's different right out of the gate. So we do have 1 chiral atom there. If we go through and look at all the other positions, you'll notice that we can't have chiral atoms. The carbons of the double bond only have 3 groups of electrons. They can't be chiral. Okay? The carbons of the rest of the ring attached to 2 hydrogens. We can't tell a difference between the hydrogens. Okay? What happens when we move to the next example? Here's this weird trigger that jumps in there. Remember we said, we've got a wedge. We've got a wedge, that must mean chirality. But remember, wedge and dash should be used if we have a chiral molecule. It is not necessarily a requirement, depending on what we're looking at. It is also not a requirement to not show a wedge or a dash if it's a chiral molecule or an achiral molecule. In this case, we have an internal mirror plane, which at least one person saw. Okay, the internal mirror plane negates the chirality. So we have an achiral molecule in that case, no stereocenter. The other option is going through and looking at our differences. We've got our hydrogen and our chlorine, which would both be 4. If we look at our carbon, or sorry, that's a nomenclature coming back, sorry, call that 2. If we look at our carbon, that's definitely different from our chlorine and our hydrogen, but what about the other carbon? They're both CH2s. If we don't see a difference, what do we need to do? Go to the next atom. So we would go to the next atom and then compare these two atoms, which are CH2s. And then what do? We go to the next atom and we overlap. By then intersecting at the same point where we haven't found a difference, what does that mean? Those two are identical. We don't have 4 distinguishable groups. We only have 3. No chiral atom. Why was the wedge put on there? To confuse you. That is it. Okay? And some people flip out, well, why are you intentionally confusing us? Well, it's not so much that we're intentionally confusing you. It's that when you write answers down on a test, you will use wedges and dashes when you shouldn't need to use it. The only time you should really be using wedges and dashes is when you have a chiral molecule or a chiral atom. Okay? That's the only time it's necessary. Any other point, it's irrelevant. Since you are putting it in at a wrong opportune time, we now have to test you on when to put it in. Okay? Last one. We see no wedges and dashes, so the gut instinct is no chiral atoms. Remember, it is not a requirement to show that an atom is chiral, okay, by showing the wedges and dashes. Depends on what we're looking at. In this case, you're being asked if it's chiral, so we may have hidden it. And in this case, indeed, we did. What do you have to remember from our first exam? Hydrogens are implied. And they will be implied up to an octet. You should be able to go through and identify or look for all of your carbons. And you will notice that there are 3 positions that are of particular importance with our hydrogens. Those 3 positions are our chiral atoms. Okay? Questions about what we've done so far?
So for that last structure, the hydrogen, or the carbon that's on the top, that one's different because when you go around, you never get to the intersecting point.
We find a difference before they intersect. So yeah, let's start that out with that top one. Okay, we would go out to carbon, or CH3. So there's 1, which is different from hydrogen, which we'll call 2. We would then go out to another carbon. Is that carbon different from 1?
Yes.
Yes. Okay, so we for sure have 3. What about the carbon on the other side?
It's the same as 4.
CH2 and CH2, right? So your 3s would match. We don't see a difference. What do we have to do? Keep going. Move to the next atom. We have a CH, or a carbon bound to a hydrogen, oxygen, and carbon. And then on our other side, we have a carbon bound to 2 hydrogens and a carbon. Is there a difference between those 2 positions? What does that mean?
They're different.
Our initial are different, and we have 4 distinguishable groups. Okay. That pattern of continuing through your chain until you find that difference is incredibly important when it comes to naming these individual compounds. Okay. I have yet to record that video. We may end up, what is today? Wednesday. Hopefully that'll get recorded so you can see that, and we'll talk about that on Monday, as well as doing more spectroscopy stuff. Yes?
When it comes to like name, or like looking at the, because you said position 3 initially was the same on both sides, but then you keep looking until you find a difference.
Until you find a difference.
Or meet in the middle.
Or you come back to the middle where they overlap in that chain, and you don't find a difference,
Then that's not.
then those 2 are not different.
So for that second chiral atom, on the same as the OH, you'd have 1 as the OH, well, if you want, and then 2 as the hydrogen, 3 as the other carbon.
Keep it 3, right?
Yeah, but you could go the other way too.
So the numbering right now is completely arbitrary.
Okay. But it is different.
They are different. So if we compared those 2 carbons, they are different. We again have 4 distinguishable groups. Our red carbon is also a chiral atom. So our first structure, we had how many chiral atoms? 1. Second structure? 0. Third structure? 3. How many stereoisomers are possible for structure 1? 2. How'd you get 2? 2 to the n, where n is the number of stereocenters. We've got 1. There are 2 possible structures. For this next one, 0. I'm a little bit weird, but we'll stick with that. Last one, 2 to the third gets us 8 possible structures. Before we finalize with our 2 and our 8, what did we have to subtract or watch out for? Mirror planes. Is there a mirror plane in 1? No. Is there a mirror plane in 3? No. So we don't have to worry about any mirror planes. It's 2 and 8 for our answers. We good?
And that's why 2 to the 0 became 0 rather than 1.
Yeah, I don't even want to get into the math on that. There's still one structure. So, I mean, it doesn't, but calling it a stereoisomer doesn't work. Okay. So, questions? Okay. So let's take a look at some physical observations. Are the physical properties for a pair of diastereomers different or the same? So we've got right here a drawing representing our diastereomers. Notice one of the positions mirrored, the other one did not. So the relationship between those structures is diastereomers. Is this the only way I can look at those two structures? No. I can change my view on the molecule to look at it in a slightly different fashion, and that's what we're looking at here. These are known as our Hayworth projections. We're looking at a ring from the side. This helps us distinguish where our groups are aiming. Okay? Would we expect these compounds to have the same physical properties? What is a physical property? Give me an example. Melting point, boiling point. And those are determined based on the intermolecular forces. Well, the intermolecular forces for both these compounds we would predict to be the same, London dispersion forces. Is it just the force that we have to be concerned about? Right. If I take, I'm going to take, these are not your quizzes, by the way. I want you to panic, freak out. Intermolecular forces for these two pieces of paper are the same, right? Just pieces of paper. Okay, if I put them together like this, okay, how much interaction do I get between them? Okay, it's kind of questionable. We're trying to figure out a lot or a little. So now I ball them up. Where's the intermolecular force? The point of contact. Which one had more intermolecular forces? The first one, where they were flat. Okay? So the structure does have an effect on our intermolecular forces, or sorry, on our physical properties. Are we going to see that have an effect here? In one case, our shape is kind of hooked-ish. The other case, we have kind of a T in it. Is that going to change how those molecules can pack around like molecules? Yes. Which means the physical properties should be different. We'll get different melting points and boiling points. So if we go through an experiment where we make two structures and the relationship between those products is diastereomers, we can separate them relatively quickly and easily because they have different physical properties. Okay? So that's kind of nice when it comes to diastereomers. Okay? How might we identify which one we'd make? Melting point. Our melting points are different. So if we isolated one of them, we could look at determine what that melting point was. Okay, we could compare that to a standard, and we now know which compound we had. And what if we had both? What would happen to the melting point? I won't quite accept somewhere in between. What do you mean for
You have a broad range melting point?
We'll expect a broad range. Why is it a broad range? It's an impure compound. Okay? Where it's lower than becomes a different question. Okay? That's going to depend which one we have more of and all sorts of other things. But we should still expect a broader range because our intermolecular forces are now mixed. Okay? So, diastereomers was one of our stereoisomers. What was the other one? Enantiomers. So what if I went through, when I looked at this compound, this one was now, whoops, not that one. I gotta do the other one. This one was dashed. When I look at the Hayworth projection, what do I get?
properties but act as aqueous substances?
Now we run into an interesting issue. Number one, are they diastereomers? No. So our whole concept of diastereomers now goes out the window. We're not looking at diastereomers, we're looking at enantiomers. What about their physical properties? If we look at the shape versus, we're getting roughly the same interactions. But if I mix these two, would they be able to interact with each other the same as if they with their original? No, we're going to end up with a broad range. So our enantiomers become problematic. Okay? They have the same type of intermolecular forces and the same types of interactions as the two independent species. So we would expect the same general physical properties. But when I mix them, well, now everything goes out the window. Okay? This becomes problematic. Okay? If we had diastereomers, we could separate through distillation, which we haven't talked about, but we could boil liquids. Liquid at the lower boiling point would boil first, the other one would stay behind. So we could separate based on their phase changes. Well, here, their melting points and boiling points will be identical. How can we possibly separate them? Well, we could look at a reaction. We could try and react them. But they have the same intermolecular forces, the same general structure. If we make enantiomers, we now have a massive issue. We can't separate them easily from each other. Okay? Take it a step further. If we were to say, make a drug that had two possible stereoisomers, enantiomers, and we didn't separate them, would they interact with our bodies differently? Yes. So some nice classic examples. We had thalidomide, the other one, naproxen, pain reliever. There's two common forms for the pain reliever naproxen. One of those forms is an anti-inflammatory. Great. Okay, we can relieve our pain. The other form destroys your liver. Well, that's cool. Okay. How could we separate those two? That sucks. Okay. What about limonene? Okay, the next two compounds. This is an interesting one. One form with our chiral atom is limonene, and it smells like citrus. The other form smells like turpentine. That's a pretty big difference. Okay? And all we're doing is changing the chiral atom, the arrangement of that. When we go through and take a look at another example, these structures, enantiomers, we've got R-carvone and S-carvone, that's just representing the chiral atom. R-carvone smells like mint. S-carvone, caraway. Drastically different results in those individual scents and reactions within our body. What's your question first?
What's caraway?
The spice. That's about all I'll give you, because I don't really know beyond that. Oh, there you go. Caraway. Black licorice versus mint. If I gave you a piece of gum and said, hey, this is carvone, you'd be like, oh, it's mint. Okay, you'd be kind of pissed if you got that difference, right? So some pretty drastic differences. Why are we seeing these drastic differences? Why can we as humans detect these differences, but as chemists we suck at it? I won't go quite as far as admitting biology is awesome.
Organic sensors have been developed over 30 years.
Biology is chiral. Okay? When we look at everything, all of our biochemical molecules, all those reactions are chiral. Which then means if we take a molecule that is chiral and we interact it with another chiral molecule, they're going to get one interaction. If we now change one of them, is that going to change the interaction? Yeah. For instance, if I reached out to shake hands, which hand do you give me? Oh, you gave me the right one. Give me your left. Oh, I should twitch that. Okay. We get a different interaction, okay? Because our hands are chiral. So when it interacts with something else, we get a different result. Same thing's happening with our enantiomers. Okay? On their own, they have the same properties. If I reached out with my left, he'd still give me his left hand, right?
Maybe.
Yeah, there we go. Okay. We might be frowned upon in certain cultures for shaking hands with the left, but beside the point. Okay, we still get the same types of interactions as long as we keep our matches proper. Okay? As soon as we don't match our interactions properly, we get a different result. Okay? So when we look at our receptors in our nose, different responses. They're all chiral, which is why we can smell a difference between citrus and turpentine, even though the structure is almost identical. So the way that we're going to have to separate these is to separate them much the same way biology does. We can't just look at a bulk interaction. The bulk interaction doesn't work because the bulk interaction is achiral. Okay? We have to have them interact with something very particular. That very particular something needs to be chiral. If I now introduce that second chiral molecule, I can now separate them. And that becomes interesting. Why can I now separate them? Okay? So, which is almost on here. So let's go through in our synthesis if we're going to later do our experiments and we're going to make something. The very first thing on how to separate enantiomers, it's a pretty obvious one. Don't. Don't make enantiomers. Do whatever you can to avoid that happening because once it's happened, it sucks to separate them. Okay? So that is one option to avoid this issue. Okay? The next one is separate on a chiral medium. Okay? So next week we'll be looking at column chromatography. The column chromatography that we look at is achiral. If we make it chiral, it will allow a separation. Okay? The last one is what we just talked about in the biological sense, is react them with a chirally pure compound. Okay? What does that mean? Okay? So number one, we have tartaric acid here. Okay? Shown as RR tartaric acid. It's in reference to where those groups are. Some fun little history on tartaric acid. Anybody know? It's the original chiral molecule discovered by Pasteur. Okay, he was being paid by some viticulture people, some people making wine, and they noticed they had these crystals in the end of all of their winemaking processes, and it was tartaric acid, and they told him to start analyzing it. So he started playing around with it and noticed that if he made tartaric acid on his own, okay, he got certain properties. If he took the tartaric acid from the wine process, he had different properties. It's kind of bizarre. Why would that happen? Okay. What he ended up discovering is that when he synthetically made tartaric acid, he made two forms of it. He made the right-handed form and the left-handed form. And in the wine barrels, we only made, say, the left-handed form. That's why we had the mix of two different properties. How did he go through and test this? The one that he made, he noticed that as you crystallize the crystals, or crystallize tartaric acid out, certain crystals took on different shapes. So we painstakingly looked through a microscope and said, that crystal looks different, I'm going to put it over here. That crystal looks like that one, I'm going to put it over there. That crystal looks different, until he collected enough of a sample of each that he could then test them independently of each other. Yeah, that's fun, isn't it? Okay. So next time you pull out your crystals, any solid compound in the lab, think about going to go individually separate those crystals. Okay. So once we've got it pure, thank you, Pasteur, with our tartaric acid, we notice that we have on our far left enantiomers, right? We have a single chiral atom that has exchanged its location. I will react that with this now pure tartaric acid. Okay. When it reacts, the acid portion will react with the basic portion, and we will end up with these two possible compounds. What is the relationship between these two compounds? And some people have a hard time with that salt there. So what we can do is clean that up and say no longer make it, oops, that was a really heavy erase. Let's not make it a salt, let's just make it a straight up bond between the nitrogen and officially the carbon. No, officially the oxygen, actually. Frick, too many erasers. Make that a bond. Make that a bond. What is the relationship between those two structures? Okay. We went from wedge to dash. So at that position, okay, if we split our molecule kind of in half, we're going to actually split in 3 locations. At this position, they're mirror images. What about in that next column? Identical. And in the next column? Identical. For the relationship between these two structures to be mirror images, what has to be true at every single one of those points? They must be mirror images. Are they all mirror images? No, which means the relationship between them is? They are now diastereomers. Why is this now super, let's just do with DIAS. Diastereomers have different intermolecular forces. We can now separate those two compounds with relative ease. Okay? That doesn't change the fact that we now also don't have our compound because we've now added a thing to it. Okay? But what type of reaction did we do? Acid-base. What's special about acid-base reactions? They're reversible. So once I've got them separated, I can then reverse the process right back to where I started. I now have them separated from each other. Okay? Why is this not a really good idea? Why would we do this instead of, say, number 1? Or why would we do 1 instead of 3? What happens every time you touch chemicals? Or let's say a politician touches money. It disappears. Every time you do a reaction, you lose some product. If we started with, say, 100 things here, by the time we move to this next step, we may have lost some, let's say 10%. That's still not our final product. We have to do another reaction. Or we actually have to do a separation now between these two. So we'll lose another 10%. Okay, so now we've lost 20% of our starting compound. Okay, then we actually have to get it back to where we started. There's another 10%. So by going through and doing more chemistry, we lose product. Generally not a good idea unless we can avoid it, or unless we can't avoid it. Okay? Questions about that? By the way, I would just like to say, good job on catching the diastereomers. Took a little bit to pick that up, but that's a hard relationship to see. Okay? The last thing we can do is pretty much just accept that we suck. We've made enantiomers. We just need to report that we have enantiomers. Okay, so what we will report is something known as the enantiomeric excess. So there are two versions of our enantiomers. Okay, so what we'll do is take the highest enantiomer and we'll subtract the percentage of the lowest enantiomer and we report that as our enantiomeric excess. Okay. So if we had a system where I made 50% of one and 50% of the other, what's my enantiomeric excess? 0%. I really, really sucked. Okay? So when it comes to an enantiomeric excess, we want a really high number. We want it to be up at 100. Okay? That would be our ideal circumstance. Questions about that?
Unless we wanted specifically like the left-handed versus the right-handed, and we got a higher amount of the right-handed.
But remember, it's always highest minus lowest. So it'll always be a positive value.
I'm just saying, the higher number might be a bad thing in that specific
Oh, I see what you're saying. Yeah.
instance.
Okay. So all fine and dandy on this. And with 2 minutes, we're going to... Really? Is that what the next slide is? Yeah, it is. Okay. So we've now established that we have two different structures. We know the relationship. Okay. We now open up the next can of worms. We want to be able to identify that we have that. So what do I mean by that? You go through and run a reaction, you can just look at it and you say, oh, well, one is wedged and one is dashed. I have enantiomers, right? You just look in the reaction container. Oh, yeah, it's wedged. It's coming at me. Okay. We can't see those molecules. We have to come up with some way to be able to identify that that is indeed what happened. Okay? And this ultimately comes back to how Pasteur was able to determine and separate these. What we found is that if we take plain polarized light, I know that sounds kind of weird, but plain polarized light, and we shine it at a sample of these compounds, the light will interact with a chiral molecule. Okay? And it interacts differently for each of the different hands. Okay? What we're talking about is something known as optical activity. So we take our light sample, we filter it, clean it up so we only get one signal. It's going to have all directions of light associated with it. We pass that through a filter that removes everything else, a polarizing filter, like your fancy sunglasses, okay? So that only one axis of light passes through. Okay? If you actually have polarized sunglasses, you can take two pairs, right? You line them up next to each other and you see straight through them. What happens if you turn them 90 degrees? No light passes through. Interesting. Why? Because we've removed all the other light on that axis. One removed it on one axis. As soon as you turn them 90, it's removed it from that same axis. You can't see anything. Okay? We then take that polarized light and we aim it at our sample. If our sample is chiral, it will interact with that light and cause it to rotate off axis. That rotation we can detect, and we report as the optical activity. Okay? Depending on which way the light rotated, we name it something else. So two big names come out of this. Levorotatory, which we did signify with a negative. Dextrorotatory, which we signify with a positive. If we go back to that previous slide, notice that, oh, never mind, ignore that. I didn't put it there. Okay? Some of our chiral compounds, you will see, particularly biological ones, you'll see plus and minuses associated with them. What they're referencing is how did the sample rotate light. Okay? That's it. Levorotatory means rotates to the left. If we go on a number line and we move to the left, we move to negative numbers, hence the negative. Dextrorotatory means to the right. If we look at a number line and we move to the right, positive numbers. Okay? We can then quantify that with the degrees with which it's moved. We'll pick up there on Wednesday. Look for a nomenclature video, in particular talking about how we would name these compounds differently.
You mean Monday, right?